This video is going to be about a velocity selector. Now, velocity selector is usually the front part of a mass spectrometer. It's used for other things too, but here's the idea. If I've got a particle and I want to do some kind of a measurement on it, most things require me to know the speed of my particle. The problem with charged particles is that they tend to be really small, and things that are really small, it's hard to measure their speed. We can't just get out some kind of a radar gun or something like that. So we need to come up with some clever way of doing this. We could say, you know what, let me put some plates on here. Let me put like a big positively charged plate right here, positive potential, and that's going to get this particle and cause it to accelerate down a tube maybe, and that's great, but we still don't know the end speed because we don't know the starting speed of these particles. We don't have like a single particle that we put in this location with particle tweezers and then let go and it's released from rest and now it accelerates, and we know these things. It's really particles are moving with any kind of random motion. We don't know really what they're doing. This one could start off standing still, it could start off moving in that direction, it could be moving backwards, and either way, or if it's already moving forward, we're going to speed it up more. We don't know what it's doing. So we have this idea of a velocity selector, and the idea is this: we have a long entry tube and then we have an exit tube over here. And it's nice when these tubes are longer and narrower. In between, in the middle here, we're going to have a region where we do this. We build maybe some kind of a chamber, and we can put in this chamber a positively charged plate and a negatively charged plate. So if we can put some amount of electric potential across this thing, then that produces an electric field. Now when my particle comes through, it's coming in, and it wants to go this way, and it's going to crash into my bottom plate. Now the particle doesn't come out the other side, and that's kind of good. This thing experiences a force that's equal to Q times the electric field, and the electric field, as we know, is a difference in potential over the distance between the plates. So we need a distance between these plates. We get a force, and that gets us to move downward. So if I draw a quick free body diagram for my particle right now, I've got this electric force that points downward that's making me run into the wall. We do have a different force that is speed dependent. If I can get this thing to also experience an upward magnetic force, then it's possible that I can fine-tune these so that these two cancel out. So let's see what that looks like. To get an upward magnetic force with a charged particle moving to the right, I'm going to need a magnetic field that points into the screen within this region. The magnetic force is going to be a QVB. I can get these two to cancel out when I can say that Q times the electric field equals Q times the speed times the B field. The Q part of this cancels, so that's nice. This will work for any charged particles, but I need to come up with some kind of a way of recognizing what's going on with this speed. So when these two are going to be balanced, I've got that a speed is equal to E over B. Now the electric field from this equation back here, I can control that electric field carefully. I can fine-tune that, changing the distance between the plates or measuring it, that's easy. Changing the potential difference between the two plates usually involves a dial. The magnetic field is the same story, it's just a dial, so I can choose what speed of particle makes it through. If my particle is moving too fast, the magnetic force depends on the speed. The electric force does not. So if I'm moving too fast, I'm getting too much magnetic force, and I'm going to run into this top plate. If I'm moving too slow, then I don't have enough magnetic force to cancel out my electric, and I run into this bottom plate. But if I can Goldilocks this thing through, I'm going to get particles that move exactly the right speed, travel right through, and once they make it through, once I'm out of that chamber, now they can just continue through, and they come out the other side at exactly a known speed. What this allows me to do is to take over here a bucket of particles and just kind of throw them at the left side of this velocity selector. Now we do it a little bit more scientifically than that and release them into a chamber that then is accelerated up or whatever. But effectively I'm taking this bucket of particles, throwing them at the left side of this. Some of them will be moving at the right speed, some will be moving too fast and they won't make it out, some will be moving too slow and they won't make it out, but some will be moving the right speed and they make it all the way through. It's a velocity selector because it selects the ones that are going at the right speed. It's not a velocity controller. But that's all I'm doing with this. If I'm given some of these parameters, if I'm given the electric field and the magnetic field, I can tell you the speed of the particles that make it through. If I'm not given the electric field, but I'm given the potential difference and the distance between the plates, I can use this guy to find the electric field, then come down here and find the speed of the particles that make it through. And that's a velocity selector.